somewhere above your roof right now. A signal is not arriving. Not because the universe lacks the scale to produce it. The observable cosmos contains more stars than there are grains of sand on every beach on Earth, orbited by planets numbering in the trillions, scattered across a span of nearly 14 billion years. By the mathematics alone, the sky above you tonight should be busy with the evidence of others. Signals, structures, something reaching us across the dark. And yet the sky is quiet. It has always been quiet. 60 years of listening with the most sensitive instruments our civilization has ever built. And the answer has been the same every single night. Nothing confirmed. Nothing verified. Nothing that holds. Get comfortable now. If the lights are still on, let them go. If the day has left something unfinished sitting on your chest, set it down. You will not need it tonight. Here is what I want to be honest with you about before we begin. The silence of the universe is one of the most important unanswered questions in science. And the reason it deserves the word terrifying is not the kind of terrifying that lives in nightmares. It is the kind that arrives quietly, in the middle of an otherwise ordinary thought. When you realize the math is not adding up, the kind that belongs to an empty answer where a full one should be. That is where we are going tonight. Slowly, together. Settle in. We begin now. There is a sound playing right now that you cannot hear. Not because your hearing is limited, though of course it is. Not because the signal is too faint, though some of them are, but because after more than 60 years of pointing our most sensitive instruments at the sky, of scanning hundreds of millions of frequencies across dozens of countries on every continent, the sound is simply not there. No pattern, no repetition, no structure rising above the noise of the cosmos, no confirmed signal of any kind. This is worth pausing on, because we live in a world that moves so fast that silence tends to get filled in before we notice it. We assume the absence of an answer means we have not looked hard enough yet. We tell ourselves it is a matter of time, a matter of better technology, a matter of pointing the antenna in the right direction. And maybe that is true. Science always leaves that door open. But it is worth being honest about what we actually know right now. Tonight, in this moment, we have been listening formally and systematically since 1960. That was the year a young astronomer named Frank Drake pointed a radio telescope in Green Bank, West Virginia, at two nearby sun-like stars and listened for 80 hours. He called it Project Ozma, named after the princess of the fictional land of Oz, a place that was, in his words, very far away, difficult to reach, and populated by strange and exotic beings. He heard nothing meaningful, but what he started did not stop. In the decades that followed, the search expanded. New telescopes, new algorithms, new frequency ranges. The SETI Institute, formally established in 1984, has run continuous searches ever since. The Allen Telescope Array in Northern California, funded in part by Microsoft co-founder Paul Allen, was built specifically for this purpose. In 2016, an entrepreneur named Yuri Milner announced Breakthrough Listen, committing $100 million over 10 years to the most comprehensive search in history, covering 1 million nearby stars, the center of our galaxy, and 100 nearby galaxies, scanning across billions of frequency channels simultaneously. $100 million. 1 million stars. billions of channels. Still no confirmed signal. Now, here is where the silence starts to feel unusual. Because the universe is not young. Our sun formed about 4.5 billion years ago, and by that point, the Milky Way had already been running for roughly 8 billion years. That means there were stars like our sun forming, aging, and potentially nurturing planets billions of years before Earth even existed. If even a small fraction of those older systems produced intelligent life, and if even a small fraction of that life developed the ability to communicate across space, something should be reaching us by now. The timescales alone make absence remarkable. The astronomer Carl Sagan, writing and speaking about this question throughout the 1970s and 80s. I framed it this way. The universe is a very big place. If we are alone in it, that seems like an awful waste of space. He was not making a theological argument. He was making a statistical one. The numbers point toward company. The sky replies with silence. And here is the thing about silence. The longer it goes on, the louder it becomes. Most of us have never really sat with the weight of this. We hear it as background fact. An interesting piece of trivia. A premise for science fiction. But tonight, we are going to let it be what it actually is. A genuine mystery. One that scientists, philosophers, and mathematicians have been quietly unsettled by for decades. Because the silence is not just a gap in our knowledge. It is a shape, and the shape, once you start to trace its edges, begins to say something. We do not yet know exactly what it is saying. That is what we are here to find out. So let the room be quiet around you. Let your breathing slow. You are in exactly the right place for this kind of thinking. Somewhere between waking and drifting, where big questions tend to land softly and stay long after the night is over. The universe has been silent for a very long time. Tonight we begin asking, why? Picture an ordinary afternoon in the high desert of New Mexico. The year is 1950. The sun is hard and pale over the mesa at Los Alamos, a place that 5 years earlier had helped end the most destructive war in human history. A group of physicists is walking to lunch. The mood is easy. Someone has mentioned a cartoon making the rounds in a popular magazine. A drawing of cheerful aliens piloting flying saucers and stealing garbage cans off the streets of New York City. There is laughter. There are loose theories about the newspaper headlines that summer, full of stories about strange lights over the American West. The group settles into the cafeteria the way lunch groups always do. Trays slide along metal rails. Chairs scrape the floor. Conversations break into smaller conversations. For a while, it is just lunch. Then a man sets down his fork and asks a question out loud. Where is everybody? His name was Enrico Fermi, born in Rome in 1901. He had won the Nobel Prize in Physics in 1938 for his work on nuclear reactions. He had built the world's first nuclear reactor beneath the stands of a sports stadium at the University of Chicago. He was known among colleagues for the almost unsettling precision of his mental arithmetic. He was the kind of person who could estimate the explosive yield of a nuclear detonation by dropping scraps of paper into the shockwave and calculating how far they traveled before hitting the ground. When Fermi made a rough estimate, it tended to be right. What he had been calculating quietly, somewhere between the laboratory and the cafeteria, had nothing to do with anything on his desk that day. He had been thinking about the stars, specifically about time. The Milky Way is roughly 13 billion years old. our Sun came into existence only about 4.5 billion years ago, well into the galaxy's middle age. That means there were stars, like ours, forming billions of years earlier, with billions of years of head start on everything that followed. If any of those older systems had produced life, and if that life had developed technology even modestly faster than we have, they would have had incomprehensible amounts of time to spread, to build, to signal, to arrive. And yet here, at a lunch table in New Mexico, surrounded by some of the most brilliant scientific minds of the 20th century, no one had ever received a message. No probe had appeared in our solar system. No signal had broken through the noise of the cosmos with any structure that could not be explained by physics alone. Where is everybody? His colleagues laughed. It seemed on the surface like a joke. But those who knew Fermi understood that when he asked a question with that particular tone, he was not making small talk. He was pointing at something real. The physicist Emil Konopinski, who was present at that lunch, later recalled in subsequent accounts that Fermi had followed up with a back-of-the-envelope calculation, estimating how long it might take a civilization with modest spacefaring technology to spread across the galaxy, even without faster-than-light travel. According to Konopinski's recollections, Fermi arrived at a figure somewhere in the range of a few million years, which sounds enormous by human standards. But against a galaxy that is 13 billion years old, a few million years is an eye blink. It is a rounding error. If the galaxy is old enough to have been crossed many times over, and if the conditions for life are not impossibly rare, then someone should have made that crossing. Someone should be here. Or, at the very least, someone should be detectable. No one is detectable. This became known as the Fermi Paradox, though Fermi himself never wrote it up formally. He died of cancer in 1954 at the age of 53, only 4 years after that lunch. The paradox carries his name because of what that casual question revealed. Not just a gap in our knowledge, a genuine contradiction between what the math suggests should exist and what our instruments have ever actually found. More than 70 years later, the contradiction has not resolved. It has deepened. Every new telescope we build, every new method we develop for detecting planets around distant stars, every new calculation we run on the age and size of the galaxy only makes the silence more pronounced. The search keeps expanding. The silence keeps holding. And the question Fermi asked over a cafeteria tray in New Mexico keeps echoing through every serious conversation about our place in the universe. Where is everybody? We are going to spend the rest of tonight following that question carefully, not rushing toward an answer, not pretending the answer is simple, but following it the way you follow a path through unfamiliar country, one step at a time, trusting that the shape of the land will become clear as we move. For now, let the question settle into you. It has been waiting more than 70 years. It can wait a little longer while you breathe. Before we can truly feel the weight of the silence, we need to understand the size of the stage it is playing on, not the polite, abstract acknowledgement that the universe is large, not the familiar nod we give when someone says the numbers are incomprehensibly big and we agree and move on without really going anywhere. Tonight we are going to let the scale land properly, because the silence only becomes remarkable once you understand how many chances there were for it to be broken. Start here, right now, as you are lying still. The Milky Way contains somewhere between 100 billion and 400 billion stars. That range exists not because astronomers are guessing, but because counting individual stars in a galaxy you are sitting inside is genuinely difficult. The way it is difficult to count every tree in a dense forest when you are standing in the middle of one. The working figure used by most researchers, according to NASA and the European Space Agency, is approximately 200 billion stars, 200 billion suns, most of them older than ours. Now consider planets. For most of human history, we had no direct evidence that other stars had planets at all. That changed in 1992, when astronomers detected the first confirmed planets orbiting a pulsar using subtle rhythmic changes in the star's timing signal. 3 years later, in 1995, Michel Mayor and Didier Queloz at the University of Geneva detected the first planet orbiting a sun-like star, a discovery that eventually earned them the Nobel Prize in Physics in 2019. Since then, the count has grown faster than almost anyone expected. As of the most recent data from NASA's Exoplanet Archive, astronomers have confirmed more than 5,500 exoplanets, with thousands more candidates awaiting verification. More importantly, analysis of data from NASA's Kepler Space Telescope, which observed more than 150,000 stars between 2009 and 2018, led researchers to conclude that, on average, stars in the Milky Way host at least one planet. On average, at least one, across 200 billion stars. But planets alone are not the whole picture. What matters for life, as far as we currently understand it, is whether a planet sits within what astronomers call the habitable zone, the range of distances from its star where liquid water could theoretically exist on the surface. A 2013 study published in the Proceedings of the National Academy of Sciences, based on Kepler data and led by researchers at the University of California, Berkeley, and the University of Hawaii, estimated that approximately 22% of sun-like stars in the Milky Way host an Earth-sized planet in the habitable zone. 22% of 200 billion is roughly 44 billion potentially habitable Earth-sized planets. In our galaxy alone, pause on that number for a moment, 44 billion. In one galaxy, and we have not left our galaxy yet. Earlier estimates, based on deep field imaging from the Hubble Space Telescope, including a widely cited 2016 analysis led by Christopher Consolis at the University of Nottingham, suggested the observable universe might contain as many as 2 trillion galaxies. More recent measurements, using data from NASA's New Horizons spacecraft, have led some researchers to revise that figure, and the true count remains an active area of investigation. Whatever the final number proves to be, the total count of potentially habitable planets in the observable universe runs into figures that have no meaningful name in everyday language. Now add time. The universe has been running for 13.8 billion years. According to measurements from the European Space Agency's Planck satellite, Earth is 4.5 billion years old. That means for more than 9 billion years before our planet even formed, there were stars, planets, and the raw chemistry of life distributed across the cosmos. If life tends to arise wherever conditions allow, which is an open and genuinely contested scientific question, but a serious one, then civilizations could have been emerging and potentially reaching technological capability for 9 billion years before the first human being ever looked up at the sky. 9 billion years of possible head start. Here is what that means for tonight. When Fermi asked where everybody was, he was not asking a casual question. He was pointing at a mathematical tension sharp enough to cut through every comfortable assumption we carry about our place in the universe. If the numbers suggest that life might be common, and if the timescales suggest that technological civilizations could have had billions of years to make themselves known, then the silence is not just an absence. It is a clue. Something is keeping the universe quiet. Working out what that something is turns out to be one of the deepest, strangest, and most unexpectedly personal questions that science has ever tried to answer. We have the stage. We understand the scale. The next step is to look at the framework that tried to put a number on all of this and discover what it actually tells us when we look at it honestly. In 1961, 11 years after Fermi asked his question over lunch, a young astronomer named Frank Drake stood at a chalkboard in a conference room in Green Bank, West Virginia, and wrote down 7 symbols. The room held only a small gathering of scientists. The first serious academic conference on the search for extraterrestrial intelligence. Drake had written the equation not as a grand announcement, but as a practical tool, a way to organize the morning's discussion, to give the group a shared framework for thinking through what they did and did not know. He could not have predicted that those 7 symbols would still be generating conversation 60 years later. The Drake equation attempts to estimate the number of technologically advanced civilizations in the Milky Way that might be capable of communicating with us right now. It does this by multiplying a series of factors together. The rate at which new stars form in our galaxy, the fraction of those stars that have planets, the fraction of those planets that could support life, the fraction where life actually emerges, the fraction where that life develops intelligence, the fraction that develops technology capable of sending detectable signals into space, and finally, the average length of time such a civilization survives and continues to transmit. Multiply all of those together and you get a number. The problem, the beautiful and deeply unsettling problem, is that almost every variable in that equation is one we cannot currently measure with any confidence. Drake himself plugged in estimates and arrived at roughly 10 communicating civilizations in the Milky Way at any given time. Carl Sagan, using more optimistic assumptions, arrived at numbers in the millions. Others, using more conservative estimates for how often intelligence emerges or how long civilizations survive, have calculated results approaching 1, meaning us, possibly alone in the entire galaxy. The same equation, different honest assumptions, answers ranging across millions. That range is not a failure of the equation. It is the equation working exactly as intended, because the Drake equation was never really designed to give us a number. It was designed to show us precisely where our ignorance lives. Each variable is a door. Behind some of those doors, science has made real progress. We now know that planets are common. We know that the chemical building blocks of life, amino acids, organic molecules, the precursors to everything biology runs on, exist throughout the cosmos. They have been found in meteorites, in the gas clouds between stars, in the atmosphere of Titan, Saturn's largest moon. The universe is not chemically hostile to life. But then you reach the doors that science has not yet opened. How often does life actually begin once the ingredients are present? We have exactly 1 data point: Earth. And Earth is not a neutral sample. We cannot look at our own planet's history and conclude that life arises easily everywhere, because we are only here to ask the question precisely because it did arise here. This is what researchers call the anthropic bias, and it means our single example tells us far less than it appears to. How often does simple life develop into complex life? On Earth, single-celled organisms dominated for roughly 3 billion years before anything multicellular appeared. 3 billion years. Nearly 2/3 of Earth's entire history. Before the first animal-like organisms emerged, that transition may have required a specific and unlikely sequence of events. Or it may be close to inevitable given enough time. We genuinely do not know. And then there is the final variable, the one that sits at the end of the equation, like a quiet warning. Drake called it L, the average length of time a technological civilization survives and remains detectable. L is the variable that controls everything. You can be as optimistic as you like about the emergence of life and intelligence. But if civilizations tend to go quiet shortly after developing the ability to communicate, then L is small. And if L is small, the equation collapses towards zero, no matter how generous you are with everything that came before. When Drake made his original estimates in 1961, he suggested L might fall somewhere between 1,000 and 100 million years. That range alone tells you something. A factor of 100,000 separates the pessimistic end from the optimistic end of a single variable. Here is what makes L different from every other variable in the equation. L is not a question about distant stars. It is a question about us, about whether intelligent species tend to survive their own technological adolescence, about whether the same capacities that produce the curiosity to reach for the cosmos also produce the forces that eventually end civilizations. Drake wrote an equation to count alien civilizations, but hidden inside it, in that last variable, written on a chalkboard in West Virginia in 1961, was a question about the future of our own. Let that sit for a moment. Frank Drake passed away in September of 2022 at the age of 92. He spent his entire career listening for signals that never came. But the equation he wrote in a few minutes to organize a morning discussion has outlasted everything else from that day, because it pointed at something real, not an answer, a shape, a set of questions that grow more urgent the longer they go unanswered. We now have the stage, and we have the framework. What we need next are the explanations. Because in the decades since that chalkboard in West Virginia, researchers have not simply shrugged at the silence. They have proposed answers. Some of them are reassuring, some are not, and a few. When you sit with them long enough in a quiet room, have a way of changing how you see the night sky in ways that do not entirely reverse by morning. Suppose the silence has a reason that has nothing to do with absence. Suppose it has everything to do with choice. In 1973, the astronomer John Ball published a paper in the journal Icarus, proposing what he called the zoo hypothesis. His argument was disarmingly simple. Advanced civilizations, if they exist, and if they have had time to develop beyond our current level, may have made a deliberate decision not to contact us, not because they cannot, not because we are invisible, but because they are watching, waiting, leaving us to develop on our own terms. The way a careful researcher observes a wild ecosystem without disturbing it. The zoo analogy is uncomfortable by design. It implies we are the exhibit, that the silence around us is not empty space, but managed space. That something out there has looked at us and decided, for reasons we cannot access, that the most valuable thing to do is nothing. Sit with that for a moment. A universe deliberately kept quiet around us. Managed silence. A choice made on our behalf by something we have never detected. Now turn it over. What if the silence is not about their choices at all? What if it is about our ears? This is sometimes called the interstellar miscommunication argument. And it has a disquieting logic. We have been searching for radio signals because radio was the long-range communication technology we developed first. We assumed, reasonably, that any civilization reaching out to others would use the most efficient and universally recognizable method available. But consider how quickly our own technology has shifted. In 1900, intercontinental messages traveled by telegraph cable. By 1950, by radio. By 2000, by the internet. Today, most human communication no longer leaks meaningfully into space at all. Our electromagnetic footprint has been shrinking in intensity as we move toward more efficient, more tightly directed networks. If we have made that transition in barely a century, a civilization 1,000 years ahead of us may be using communication methods we do not yet know how to search for. We would have no way of detecting any of it. Not because the signals are not there, because we are listening in entirely the wrong way. The way someone pressing their ear to a wall might conclude the building is empty while everyone inside communicates through channels that leave no mark on plaster. Here is where these two explanations begin to press against each other in an interesting way. The zoo says, someone is out there and has chosen silence. The radio says, someone may be out there, but we simply cannot hear them. Both produce the same surface result. Both are internally consistent. Both are impossible to rule out with the evidence we currently have. And yet they point in completely opposite directions about what we should do next. One says we need to wait and become worthy of contact. The other says we need to build better instruments and imagine harder. We cannot tell which is right. We may never be able to. And then there is a third layer, one that quietly undermines both of the first two from a direction neither of them anticipated. The astronomer and long-time SETI researcher Jill Tarter has argued over decades of work that our search strategies are inevitably shaped by our own cognitive and technological horizons. We search for what we can imagine, and what we can imagine is bounded by what we are. Every detection strategy we design assumes that an advanced civilization will want to be found in a way that instruments like ours can find them. But that assumption is a mirror. We are looking at ourselves and calling it a map of the universe. An intelligence that has had 1 billion years to develop might differ from us as profoundly as we differ from the simplest organisms alive on Earth today. Not hostile, not indifferent in any emotional sense. Simply operating at a level of complexity and on timescales so different from ours that the concept of communication, as we understand it, may not cleanly apply. What makes this third layer so unsettling is that it does not just add a third explanation to the first two. It questions whether our ability to evaluate any explanation is itself limited in ways we cannot fully see. The zoo might be real, and we would not know. The wrong frequency might be real, and we would not know. The silence might be something we do not yet have a word for. 3 explanations. A deliberate choice. A failure of our instruments. A gap between what we are and what might be out there. Each one plausible. Each one impossible to confirm. Each one, when followed far enough, stops being about them entirely and starts being about us. That is where we are going next, into the explanations that reach past the stars and land, quietly and with considerable force, right here. There is an assumption so deeply embedded in the way we think about the universe that most of us have never noticed it is there. The assumption is this: Earth is ordinary. It sounds humble. It sounds like good science. After centuries during which Western thought placed Earth at the literal center of the cosmos, the correction feels appropriate and long overdue. We learned that our planet orbits a star. We learned that our star is one of hundreds of billions in the galaxy. We learned that our galaxy is one of an enormous number in the observable universe. Each discovery pushed us further from the idea that we occupy any special position, and so we arrived at what scientists call the Copernican principle, the working assumption that Earth is a typical planet, our Sun a typical star, our position in the galaxy unremarkable. If Earth is ordinary, then what happened here should be happening elsewhere. But what if Earth is not ordinary? In the year 2000, the paleontologist Peter Ward and the astronomer Donald Brownlee, both at the University of Washington, published a book called Rare Earth: Why Complex Life is Uncommon in the Universe. Their argument was precise. Simple microbial life, they suggested, might indeed be widespread. But complex life, the kind that eventually builds cities and telescopes and asks questions about its own existence, may require a combination of conditions so specific and so unlikely to occur together that it has emerged only a handful of times in the observable universe. Or possibly only once. The conditions they identified are worth moving through slowly, because the power of the argument is cumulative. Begin with where we are in the galaxy. Our solar system sits in what astronomers call the galactic habitable zone, a band roughly 25,000 to 30,000 light-years from the galactic center. The center of the Milky Way is a violent neighborhood. It contains a supermassive black hole, dense clusters of stars, intense radiation fields, and a much higher frequency of supernovae, the explosive deaths of massive stars that can strip away planetary atmospheres across vast distances, the outer edges of the galaxy. On the other hand, lack the heavier elements produced by multiple generations of stellar evolution, elements necessary to build rocky planets and complex chemistry. Our position in a relatively calm spiral arm, chemically rich and radiatively quiet, is a circumstance. It is not a given. Now consider our star. The Sun is unusually stable compared to many stars of similar mass. It does not flare frequently or violently. It has maintained a relatively consistent energy output over billions of years. This matters because the development of complex life on Earth took roughly 4 billion years, and a star that varied significantly over that timescale would have repeatedly disrupted the climate stability that development required. Most stars in the galaxy are smaller and cooler than our Sun, and while many are now considered serious candidates for hosting habitable planets, they tend to flare more intensely relative to their luminosity, potentially bathing nearby planets in radiation during precisely the early periods when life would be most vulnerable. Then there is the Moon. Earth's moon is extraordinarily large relative to its host planet, far larger in proportion than the moons of most other planets we have studied. The moon stabilizes Earth's axial tilt. Our planet leans at approximately 23.5 degrees relative to its orbital plane, and that tilt produces the seasons and the moderate climate patterns that complex life depends on. Without the moon's gravitational steadying influence, calculations suggest Earth's axis could wander far more dramatically over millions of years. A planet whose axis swings widely develops climate extremes severe enough to challenge the survival of anything more complex than bacteria. The moon is not a decorative feature of the night sky. It is a stabilizer, a piece of quietly essential geometry that most planets do not have. And then there is Jupiter. The largest planet in our solar system sits 5 times farther from the Sun than Earth and contains more mass than all other planets in the solar system combined. Its gravitational influence has likely played a significant role in shaping the history of impacts on the inner solar system. And planetary scientists have suggested it may have reduced the rate at which comets and asteroids reached Earth. The full picture of Jupiter's role remains an area of active research, with some studies suggesting the dynamics are more complex than a simple shield. But the broad point holds. Jupiter has been part of the gravitational architecture that shaped Earth's impact history, and that history shaped the conditions in which life had room to develop. Add to this Earth's large iron core, which generates the magnetic field that shields the surface from solar wind and cosmic radiation. Add the plate tectonic system that recycles carbon and regulates long-term climate over geological time. Add the specific sequence of events that led to the Great Oxidation Event roughly 2.4 billion years ago, when photosynthetic bacteria began flooding the atmosphere with oxygen, eventually creating the conditions that allowed complex multicellular life to breathe. Each of these factors interacts with the others. Remove any one of them at the wrong moment, and the chain of events that produced us either does not happen or unfolds in a direction that does not end with anything asking questions. Ward and Brownlee's argument has been challenged and refined in the 2 decades since their book appeared. Some researchers argue they were too conservative about the range of conditions that can support complex life. Others argue they did not go far enough. The debate is ongoing, and that is exactly as it should be. But the core insight has survived. Earth may not be typical, and if Earth is not typical, then the emergence of complex life capable of building instruments and asking questions may be rarer than the sheer number of planets in the universe would suggest. Here is what makes this explanation feel different from the others. This one does not require anyone to be hiding. It does not require anyone to be communicating on frequencies we cannot detect. It does not require any choice or any deliberate silence. It simply requires that the recipe for complex life is harder to follow than it looks, and that we happen to live on a planet where, against considerable odds, every ingredient arrived in the right amount at the right time. There is something worth sitting with in that, if you let yourself feel it. Not pride, not a return to the idea that we are the center of anything. Something quieter, a recognition that what you are lying on tonight, this spinning, water-covered, magnetically shielded, moon-stabilized, improbably positioned rock, is not something the universe produces without a great deal of patience and a great deal of luck. You may not be on an ordinary planet. The mind that evolved on it is even harder to explain. Somewhere in the warm chemistry of early Earth, roughly 3.8 billion years ago, something happened. We do not know exactly where. We cannot point to a specific moment when the line between complex chemistry and living chemistry was crossed. The origin of life, what scientists call abiogenesis, remains one of the great unsolved problems in all of biology. But we know it happened, and we know roughly when, because the fossil record contains traces of microbial life dating back nearly 4 billion years, arriving not long after the planet had cooled enough to hold liquid water on its surface. That timing is remarkable, though it is easy to miss the significance. Earth formed approximately 4.5 billion years ago. For its first several hundred million years, it was a hellish place, bombarded by asteroids. Its surface partly molten. Its earliest oceans subjected to impacts large enough to vaporize them entirely. This period only began to subside roughly 3.8 to 4 billion years ago, and within a geologically short time after, conditions became survivable. Life appeared. Some biologists have argued that this rapid appearance suggests the emergence of simple life, given the right chemical environment, may be close to chemically inevitable, not guaranteed, but strongly favored by the underlying processes. If this is true, microbial life may indeed be common across the universe, arising on any world that has liquid water, organic chemistry, and enough time. But here is where the story takes its turn. For the next 3 billion years, life on Earth was almost entirely microbial. 3 billion years. Sit with that duration for a moment. The entire observable universe is only about 4.5 times older than the stretch during which the most complex thing alive on Earth was a single-celled organism. Bacteria arrived early and stayed dominant for a span of time that makes all of recorded human history look like the final seconds of a very long day. They colonized every environment on the planet. They transformed the atmosphere. They are, by every reasonable evolutionary measure, one of the great success stories in the history of life. But they did not build anything. They did not ask questions. They did not look up. The transition from simple microbial life to complex multicellular life required a specific event that appears, based on current evidence, to have happened exactly once in Earth's history, approximately 1.5 to 2 billion years ago. A single ancestral cell absorbed another cell rather than digesting it. The absorbed cell became what we now call the mitochondrion, the energy-producing structure found in virtually every complex cell on Earth today. This event, called endosymbiosis, was not a gradual trend. It was a singular biological accident that reorganized the energy economics of life and made the complexity of plants, animals, and eventually minds possible. Once, in 4 billion years, on one planet. Now, consider what followed. Complex multicellular life has existed on Earth for roughly 600 million years, a period that includes the explosion of animal diversity in the Cambrian, the rise and fall of the dinosaurs, and the entire span of vertebrate evolution. Of all the species that have ever existed across that 600 million years, intelligence capable of abstract thought, language, technology, and the contemplation of the cosmos appears to have emerged exactly once, in one branch of one order, of one class, of one phylum, us, not dolphins, though their intelligence continues to impress researchers, not crows, whose problem-solving abilities have surprised scientists for decades, not octopuses, whose nervous systems represent a completely independent evolutionary path towards sophisticated cognition, None of them built a radio telescope. None of them wrote down an equation to count the stars. We did. Once. After 4 billion years. The Harvard paleontologist Stephen Jay Gould spent much of his career arguing that if you rewound the tape of life on Earth and played it again from the beginning, the outcome would not be humans. The path that led to us required such a specific sequence of contingent events, each one depending on everything before it, that repeating it is effectively impossible. Intelligence, in this view, is not a destination that evolution tends toward. It is an accident. Not everyone agrees. The Cambridge paleontologist Simon Conway Morris has argued the opposite, that evolution tends to converge on similar solutions to similar problems, and that intelligence is a solution evolution might find repeatedly given enough time. His book, Life's Solution, published in 2003, makes the case that something like human-level intelligence may be closer to inevitable than Gould believed. This debate, contingency versus convergence, remains genuinely unresolved, and it matters enormously for the silence of the universe. If Gould is right, the silence makes perfect sense. If Conway Morris is right, we are back at the original puzzle. Where is everybody? What this chapter adds is a layer that changes how the puzzle feels, not just how it looks. Even if the universe is full of planets with microbial life, even if simple biology is genuinely common, the road from bacteria to telescope builder is not a road at all. It is a series of accidents, each one building on the last, each one dependent on conditions that may not repeat themselves elsewhere. The universe may be teeming with life, oceans full of microbes on 1,000 worlds, ancient and thriving and completely silent, not because life failed, but because the particular kind of life that reaches for answers is the hardest kind to produce. You are the result of 4 billion years of those accidents. Every single one had to happen, in the right order, on the right planet. The probability of you being here to hear these words is not just very small, it is, in any ordinary framework, incalculable. Let that settle now. Not as a weight, as something closer to wonder. You are an improbable thing, on an improbable planet, in a universe that may have tried to build something like you across billions of years of chemistry and accident and time, and succeeded only here. The silence outside may not be emptiness. It may be the sound of how rare you are. There is a question hiding inside the Fermi Paradox that most people never quite reach. Most people stop at the surface version. The universe is large. Life might be common. So where is everybody? That question is already unsettling enough. But underneath it, reached only when you follow the logic far enough and refuse to look away, is a second question, quieter, more personal, more difficult to set down once you have picked it up. If something is keeping the universe silent, what is it? And where are we in relation to it? In 1998, an economist named Robin Hanson published a paper called The Great Filter: Are We Almost Past It? Hanson was a researcher at George Mason University who thought carefully about large-scale risks and the long-run future of intelligent life. What he proposed was a framework so clean and so uncomfortable that it has become one of the most discussed ideas in the field of existential risk. The argument begins from a simple tension. We observe that the universe appears empty of advanced civilizations. We also know the universe has had enormous time and an enormous number of planets on which such civilizations could have emerged. Something must explain why the sky is not already filled with evidence of intelligence. Hansen called that something the great filter. The filter is not a specific event. It is a category. It refers to whatever step in the development from dead chemistry to galaxy-spanning civilization is so difficult, so unlikely, or so consistently destructive that almost nothing makes it through. Somewhere along the path from molecules to cosmos builders, there is a wall. Most things that attempt the climb do not reach the top. The question is where the wall is. Consider the full sequence of steps required to go from a lifeless planet to a civilization capable of being detected across interstellar distances. You need the right chemistry. You need the origin of self-replicating molecules. You need the emergence of the complex cell. You need multicellular life. You need intelligence. You need technology. You need that civilization to survive long enough to become detectable. Each step is a candidate for the filter. Some of those steps we have already discussed as potentially very difficult: the origin of life from chemistry, the transition from simple to complex cells, the emergence of intelligence from complex life. If any one of these steps is extraordinarily improbable, something that succeeds perhaps once in 10 billion attempts, it would serve as the great filter. It would explain the silence without requiring any civilization to have been destroyed. They simply never existed in the first place. This version is sometimes called the filter behind us. It means the hardest step has already been taken. We are on the far side of the wall, looking back at a universe of planets that never made the climb. If that is true, the implications are strange and beautiful in equal measure. We are almost certainly alone, or nearly so, in the galaxy. Not because the universe is hostile, but because the sequence required to produce us was so improbable, it has not been repeated within range of our instruments. That version carries a kind of quiet dignity. We made it past the hardest part. But there is another version, and this is the one that scientists lower their voices for. What if the filter is not behind us? What if it is ahead? What if the difficult steps, the origin of life, the development of intelligence, the emergence of technology, are not actually that improbable? What if they happen on many worlds, and the thing that almost no civilization survives is not the beginning of the journey, but a later stage? A stage we have not yet reached. Under this reading, the silence is not the sound of rarity, it is the sound of failure. Civilizations arise. They develop technology. They reach approximately the level we are at now. And then something ends them. Consistently, across billions of years and trillions of chances. A filter that operates late rather than early would leave no wreckage we could detect. A civilization that destroys itself does not send distress signals. It simply goes quiet. And from a distance, a dead planet looks identical to one that never had life at all. The philosopher Nick Bostrom at the University of Oxford made this point with particular clarity in a 2008 paper titled "Where Are They?" He argued, carefully and in detail, that finding confirmed evidence of simple life elsewhere in the universe would be, in one specific and counterintuitive sense, bad news for humanity, because it would mean that the origin of life is not the filter. If life arises easily, if microbial organisms are common, then the wall that explains the silence must be somewhere further along the path, somewhere we have not yet passed. This means the best possible result of our search for life on Mars or Europa or any other nearby world would be to find absolutely nothing. Because sterility suggests the emergence of life is itself the difficult step, and that we have somehow cleared it, every confirmed trace of biology we find on another world moves the filter closer to us, closer to our future, closer to whatever comes next for a civilization with the tools we currently hold. Bostrom's argument is a framework, not a prophecy. The Great Filter is not a confirmed fact. It is a way of organizing the possibilities that the silence presents, one that is internally consistent and scientifically serious. Once you have understood it, it does not entirely go away. The silence is either evidence that the hardest step is behind us, or it is a warning about what lies ahead. We do not know which, and that not knowing, sitting with it honestly in a quiet room, is not comfortable. But there is something worth holding before we move forward, because the Great Filter has two faces, and we have only looked at one of them tonight. The other face is different, not darker, in some ways stranger and more demanding, because if the worst version is a warning, the best version is something close to a calling. We will look at both in the next 2 chapters, one at a time, without flinching. For now, let the weight of the question settle where it has landed. It will still be there in the morning. Let us sit with the better possibility for a while. Not because it is more likely, we genuinely do not know which possibility is more likely, but because it deserves the same careful attention as the darker version, and because the full weight of what it would mean has not been adequately felt by most people who encounter the idea briefly and move on. If the Great Filter is behind us, something extraordinary follows. It means that somewhere in the 4 billion year history of life on Earth, a step occurred that was so improbable it has almost certainly not been repeated anywhere else within the observable universe, or has been repeated so rarely that no other civilization has yet reached the point of being detectable. That step could be the origin of life itself. It could be the emergence of the complex cell. It could be the development of multicellular organisms. It could be the specific sequence of evolutionary accidents that produced a brain capable of abstract reasoning. It could be a combination of several of these, each one unlikely on its own, their combined probability vanishingly small. Whatever it was, we passed it, and almost nothing else did. This means we may be the first, not the chosen, not the center, not special in any designed or cosmic sense, just the first. The way the first star that ever ignited in the universe was not special by intention, but was simply the formation that happened to reach the necessary conditions before anything else. Sit with that for a moment, because it is easy to hear it and nod without really letting it land. We may be the first civilization in the history of the observable universe to look up and understand what it is looking at. Every piece of music ever composed, every question ever asked about the nature of time or matter or consciousness, every act of grief and wonder and curiosity that any human being has ever felt, all of it may be the first time anything in 13.8 billion years of cosmic history has done any of these things. Not the first time on Earth, the first time anywhere. Carl Sagan returned to this feeling throughout his life and work. He described human beings as a way for the cosmos to know itself, the universe having arranged matter into a form capable of looking back and asking what it is. He was careful to frame this as poetry, not physics, but the Great Filter, in its optimistic version, gives that poetry a structural foundation. If complex intelligence is genuinely the rarest product of the universe's long experiment, then consciousness, wherever it exists, is not incidental. It is statistically extraordinary. Now consider what this version of the story says about our responsibilities. If we are among the first, then what we do next matters in a way that extends far beyond our own survival. Every civilization that will ever exist in the future of this galaxy, if any do, I will look back on this period the way we look back on the formation of the first stars, as the beginning, as the moment when the universe turned a corner it had never turned before. The physicist Freeman Dyson, writing in the 1979 essay Time Without End, and in the work that followed, argued that mind and intelligence were capable of becoming, over astronomical timescales, a meaningful force shaping the long-run future of the cosmos. He was not making a mystical argument. He was making an extrapolation from known physics, asking what an intelligence with billions of years and access to stellar-scale energy could eventually accomplish. His answer was, in the most careful and literal sense, almost anything. If the filter is behind us, the future is genuinely open, not easy, not guaranteed, but open in a way it would not be if the silence were a warning. The path ahead has not already been walked by thousands of civilizations and found to end in a wall. It is unmapped. We are exploring it for the first time. There is a specific kind of loneliness in this version of the story that deserves to be named. Being first is not the same as being safe. There is no elder civilization to receive our signals and offer guidance. No accumulated wisdom from those who have navigated this stage before. No guarantee that the questions we are struggling with now, how to manage powerful technology, how to cooperate across difference, how to build systems stable enough to last, have already been answered somewhere and found to be answerable. We are working without a net, but we are also working without a ceiling. The philosopher Toby Ord, in his 2020 book, The Precipice, argued that if humanity can navigate the current period of technological development, the potential future available to our descendants is of a scope and duration that makes all of prior human history look like a single opening sentence in a book of enormous length. He estimated that the potential value of what lies ahead for a surviving civilization is so large that the cost of extinction, measured against that future, becomes almost incomprehensible. Not just the loss of everyone alive today, the loss of everyone who would ever have lived. If the filter is behind us, that is what is at stake in the choices being made right now. Not just this century, not just this generation, the entire future of what may be, in the most literal and non-sentimental sense. A genuinely unprecedented phenomenon in the history of the observable universe. That is a heavy thought. It is also, in a strange way, a steadying one, because it means that what you do, not in some grand cosmic abstraction, but in the ordinary texture of a human life, is part of something that may have no precedent anywhere. The universe has been running for nearly 14 billion years. This moment, right now, may be the first time anything in it has had the chance to choose what comes next. Let your breathing slow. The next chapter turns the coin over. It needs to be looked at directly, without softening, but before we go there, hold this version a moment longer. The silence may not be a warning. It may be an inheritance, And the page that follows may be the first one anyone, anywhere, has ever had the chance to write. There is a version of the future that no one wants to think about too carefully. Not because it is impossible, because it might not be. We have just sat with the possibility that the hardest step is behind us, that we are the rare and improbable survivors of a gauntlet most worlds never pass. That version carries its own weight. But we owe ourselves the honesty of turning the coin over completely, because the other side is there, and looking away does not make it smaller. If the great filter is ahead of us, the silence is not the sound of rarity. It is a pattern, a consistent, repeating pattern playing out across billions of years and trillions of planets, in which civilizations reach a certain level of development and then go quiet, not because they choose silence, not because they transcend to some form we cannot detect, because something ends them. The question is, what? The honest answer is that we cannot know with certainty. We have no confirmed examples of another civilization to study. We are, by definition, survivors so far. The civilizations that failed are not here to describe how they failed, but we can reason about candidates, and the candidates, when examined clearly, are not abstract or distant. They are technologies and pressures and tendencies we already recognize. Some of them are already in our hands. Consider nuclear weapons. In 1945, humanity crossed a threshold that had never been crossed before in the known history of life on Earth. We built a device capable of destroying a city in a single detonation. Within 4 years, a second nation had the same capability. The Cold War that followed brought the world closer to civilization-ending exchange than most people alive today fully appreciate. The Cuban Missile Crisis of October 1962 was, for 13 days, a situation in which multiple senior military officials on both sides were prepared to use nuclear weapons, operating with incomplete information, under enormous pressure, in real time. On October 27th of that year, a Soviet submarine designated B-59 was operating near the American naval blockade around Cuba. The crew had been out of contact with Moscow for days and did not know whether war had already begun. American destroyers above them were dropping practice depth charges to signal the submarine to surface. According to accounts that emerged after the Soviet Union's dissolution, including testimony from former Soviet officials and declassified records reviewed by historians, the crew interpreted these as actual attacks. The submarine carried a nuclear torpedo. The captain reportedly wanted to fire it. The political officer reportedly agreed. Under the protocol in place at the time, a third senior officer's agreement was required. That officer was a man named Vasily Arkhipov. He reportedly refused. The nuclear exchange that did not happen that October, the cities that were not destroyed, the hundreds of millions of people who did not die, existed in part because of one man's reported decision in a submarine running without reliable communications, believing itself to be under attack. The full details of what was said in that vessel remain imperfectly documented, as historians continue to work from accounts that are necessarily incomplete, but the broad outline has been substantiated by multiple independent sources. That is how narrow it was. And nuclear weapons are not the only threshold we have crossed or are approaching. Engineered pathogens represent a category of risk that biosecurity researchers have documented with increasing specificity since the early 2000s. The same biotechnology that enables vaccine development and cancer treatment also lowers, year by year, the technical barrier required to work with dangerous biological agents. Researchers in the biosecurity field have argued, in peer-reviewed literature, that capabilities once confined to well-resourced, specialized laboratories are becoming more widely accessible as the underlying technology advances, a trend that has prompted serious calls for governance frameworks that have not yet fully materialized. Then there is climate change. Understood here, not as a political argument, but as a physical process with a well-documented mechanism, the Intergovernmental Panel on Climate Change, drawing on the work of thousands of researchers across dozens of countries, has consistently found that sustained greenhouse gas emissions will produce temperature increases and associated effects severe enough to stress the complex interdependent systems that allow billions of people to be fed, governed, and protected. No credible scientific body suggests extinction in the near term. But civilizational disruption does not require extinction. It requires only sufficient stress on systems that are more fragile than they appear from inside them. And then there is artificial intelligence, not the malevolent robot of science fiction. The concern that serious researchers in this field have articulated is more subtle and more difficult to dismiss. An artificial intelligence system significantly more capable than human intelligence across most domains, and optimizing for goals even slightly misaligned with human values, does not need to be hostile to be dangerous. It needs only to be powerful and to want something other than what we actually want. Researchers at organizations dedicated to understanding the long-term safety implications of this technology have argued that the arrival of systems with transformative capability represents a change in the kind of power available in the world that deserves the same quality of serious attention we give to any other civilizational scale risk. These arguments are not made to produce panic. They are made because the tools of formal reasoning suggest that this transition, if and when it occurs, is among the developments most likely to determine whether the coming century ends well or badly for humanity. Fermi's paradox may be pointing at all of this, not at any single technology, but at the general pattern that civilizations, when they reach a certain level of capability, acquire the power to end themselves before they acquire the wisdom to reliably choose not to, and that this pattern, if it is real and consistent, would produce exactly the silence we observe. A universe full of worlds that reached our level and did not make it further. This is what Robin Hanson was pointing at in 1998. This is why Nick Bostrom said that finding life on Mars would be, in one specific sense, bad news. Not because life is bad, because life appearing easily means the filter is not behind us. It is here. At the stage we are living through right now, we are not doomed. The great filter is not a prophecy. The coin that lands the same way 99 times can still land differently on the 100th, but it means the choices being made right now, in laboratories and legislative chambers, and the quiet decisions of institutions about how seriously to take the risks that previous generations never had to consider, are not simply policy questions. They are, in the framework of the filter, the most consequential questions our species has ever faced. Because if the filter is ahead, we are approaching it, and every civilization that reached this point is now silent. On the night of August 8, 1977, a radio telescope in Ohio was doing what it had been doing every night for 4 years. Listening. The telescope was called Big Ear, operated by Ohio State University. Its dish was fixed, carved into the landscape, and it scanned the sky by letting Earth's rotation carry different regions of the cosmos through its field of view. It had been running a SETI survey continuously since 1973, recording signal intensities across a narrow range of frequencies centered on what astronomers called the hydrogen line, 1.42 GHz, the frequency at which neutral hydrogen atoms naturally emit radiation. The hydrogen line had been proposed as the most logical frequency for interstellar communication by the physicists Philip Morrison and Giuseppe Cocconi in a landmark 1959 paper in the journal Nature. Their reasoning was elegant. Hydrogen is the most abundant element in the universe. Any technologically advanced civilization would know about it. A frequency derived from its fundamental emission would be a kind of universal reference point, a channel that any listener with sufficient technology would think to monitor. If you were trying to reach someone you had never met, across a distance you could not cross, you would broadcast where they were most likely to be listening. Big Ear had been listening on that channel for 4 years. Every night, every rotation of the Earth, nothing unusual had been detected. Then, on August 8th, something rose out of the noise. The signal was recorded automatically and printed out on the continuous datasheets Big Ear used to log its observations. It was not read that night. The printouts accumulated, as they always did, to be reviewed by human volunteers in the days that followed. It was not until August 15th, 7 days after the signal was recorded, that a volunteer named Jerry Eman sat down with that particular stretch of data. Each character in Big Ear's output represented a signal intensity. The number 1 meant background noise. Each step upward, through numbers and then into letters of the alphabet, represented a higher multiple of that baseline. Most of the data Eman reviewed looked the way it always looked. Background noise, the faint, consistent murmur of the universe going about its business. And then, in the middle of the page, a sequence appeared that did not look like noise. The characters read 6QUJ5 in the coding system Big Ear used. This represented a signal that had risen sharply from the background, peaked at an intensity more than 30 times above the noise floor, and then fallen away again. The entire rise and fall had taken approximately 72 seconds. 72 seconds was exactly how long Big Ear's beam would observe any given point in the sky as Earth rotated beneath it. The signal had risen and fallen in a smooth bell curve shape, precisely the pattern an astronomical source at a fixed point in the sky would produce if it were emitting a continuous signal, and Big Ear's rotating view had swept across it. The signal was narrowband, concentrated in a very small range of frequencies. Natural astrophysical processes tend to produce broadband emissions spread across wide swaths of the spectrum. Narrowband signals are considered a potential signature of deliberate transmission, because a designed transmitter concentrates its power into a specific frequency to maximize the distance at which it can be detected. It appeared to originate from a direction in the constellation Sagittarius, in a region with no catalogue star or known radio source that would explain an emission of that strength. Jerry Eman picked up his red pen and circled the sequence. In the margin, he wrote one word. Wow. Picture that moment. A volunteer, reviewing routine data on an otherwise ordinary morning, sitting alone with a printout of something that had never appeared in 4 years of continuous listening. No control room full of excited scientists. No cameras. No announcement. Just a man, a pen, and 6 characters on a page that looked like nothing he had ever seen before. He circled them. He wrote one word. And then he set the printout down. In the decades since August of 1977, Big Ear and other telescopes have pointed at that region of sky hundreds of times. The Very Large Array in New Mexico has searched the same coordinates. The Allen Telescope Array has listened. Breakthrough Listen has scanned it with instruments far more sensitive than anything that existed in 1977. No recurrence has ever been found. In 2016, a paper by astronomer Antonio Paris proposed that the signal might have been produced by the hydrogen cloud surrounding one of 2 comets passing through the region at the time. Subsequent analysis by other researchers, including scientists who had worked directly with the Big Ear project, raised significant objections. The comets had not been discovered in 1977, and their positions on August 8th of that year were reconstructed retroactively from orbital calculations. Critics argued that a comet's hydrogen emission would be broadband rather than narrowband and would not produce the intensity profile the WOW signal displayed. The comet hypothesis has not achieved broad acceptance within the relevant scientific community. The signal remains, in the formal language of the literature, unexplained. Unexplained is not the same as extraterrestrial. That distinction must be maintained honestly. There are many anomalous signals in the history of radio astronomy. Most eventually receive explanations that have nothing to do with intelligence. Pulsars, discovered in 1967 by Jocelyn Bell Burnell, were initially labeled LGM1 for little green men before being correctly identified as rapidly rotating neutron stars. The WOW signal may have a mundane explanation that has simply not been found yet. But here is the honest accounting. Nearly 50 years after Jerry Eman circled those 6 characters, the WOW signal remains one of the most widely discussed and unresolved candidates in the history of systematic sky surveys. It has not been confirmed. It has not been replicated. It has not been explained to the satisfaction of the scientific community that has examined it most carefully. It sits in the record as a single data point, a 72-second signal from the direction of Sagittarius. On the hydrogen line, narrow band, more than 30 times above background noise, rising and falling exactly as a fixed astronomical source would. Detected once and never again. Jerry Eman, in interviews over the years before his death, consistently declined to claim the signal was definitively artificial. He was a scientist. He understood what evidence requires. But he never described what he saw on that page as ordinary. He had been reading printouts for a long time. He knew what noise looked like. He wrote one word. He meant it. The telescope that recorded the signal was demolished in 1997 to make way for a golf course expansion. The land where it stood is now part of a fairway in a suburb of Columbus, Ohio. The sky it listened to for over 2 decades is still there, still full of frequencies we have not yet fully mapped, somewhere in the direction of Sagittarius, on a frequency that hydrogen atoms have broadcast since the earliest stars. Something registered once on the instruments of a telescope that no longer exists, was circled in red by a man sitting alone with a printout, and was never heard again. The search continues. Every night, in facilities across the world, pointed at a sky that has not answered. Not once. Not yet. There is a novel that changed the way a generation of readers thought about the silence. It was published in Chinese in 2008, written by a physicist and author named Liu Cixin. The English translation appeared in 2015 under the title The Dark Forest. It became one of the most widely read works of science fiction of the decade, and buried inside its pages, as the central architecture of its story, is a hypothesis about the silence of the universe that some researchers and writers have treated as a serious thought experiment, one consistent enough with known logic that it deserves to be followed wherever it leads. Liu Cixin called it the dark forest theory. The argument rests on two axioms, two foundational assumptions that the theory treats as true for any civilization anywhere in the universe. The first is that every civilization's primary drive is survival, not exploration, not communication, not the accumulation of knowledge or the expression of culture. Survival, the continuation of the civilization and the species that produced it, above all other considerations. The second is that resources in the universe are finite. Matter is limited. The usable energy available to any civilization, no matter how advanced, is bounded by physics. This means that two civilizations existing in the same universe are, at some fundamental level, in strict competition, not necessarily immediate competition, not necessarily hostile competition, but competition by the logic of scarcity, independent of intention or goodwill. From these two axioms, the theory derives a logic that is cold and precise. Consider what happens when one civilization detects another. The detecting civilization now knows another civilization exists. It does not know that civilization's intentions. It cannot know their rate of development. It cannot know whether, given opportunity, they would choose cooperation or elimination. And it cannot resolve this uncertainty through communication alone, because any communication takes time. And time spent waiting for an answer is time the other civilization has to act. The cost of trusting a civilization that turns out to be hostile is extinction. The cost of eliminating a civilization that turns out to be benign is the loss of a potential ally. When the downside of one error is your civilization's end, and the downside of the other error is merely an opportunity missed, the mathematics of survival, under these axioms, skew toward elimination, not out of cruelty, out of arithmetic. The dark forest of the title is a metaphor. Picture a vast forest at night. Every hunter in the forest knows other hunters are present. Every hunter knows that some of those others may be dangerous. The rational behavior, under these conditions, is silence, moving carefully, making no noise that would reveal your position to an unknown presence in the dark. The forest is not empty. It is full of life, but the life it contains has independently learned, through the same chain of logic. That silence is the closest thing available to safety. Under dark forest theory, the universe is not empty. It is full, but the intelligences that fill it have each arrived at the same conclusion. That announcing your existence and location to unknown others in a resource-limited cosmos is a form of vulnerability that survival logic does not permit. The civilizations that survive long enough to become powerful are precisely the ones that learned to go quiet The civilizations that announce themselves are the ones the record no longer contains. The silence, in this reading, is not absence. It is discipline. Now, this theory has been criticized on several grounds, and those criticisms deserve to be heard honestly. The economist Robin Hanson has argued that the dark forest logic overestimates the incentive to destroy and underestimates the potential value of cooperation, even between very different civilizations. Others have noted that a sufficiently advanced civilization might have access to energy and resources so far beyond what a younger civilization could offer or threaten that competition would be economically irrational. These are genuine objections. But the theory holds a particular kind of staying power, because it does something the other explanations do not. It makes the silence feel active rather than passive, not an empty universe, a quiet one. And then there is the implication that brings this thought experiment closest to home. On the afternoon of November 16th, 1974, a group of scientists at the Arecibo Observatory in Puerto Rico aimed the largest radio telescope on Earth at Messier 13, a dense cluster of stars in the constellation Hercules, approximately 25,000 light-years away, and pressed a button. A signal left this planet at the speed of light. Picture Frank Drake in that moment, standing near the instrument, knowing the signal would outlast every person in that room, every institution, the telescope itself, knowing it would still be traveling through space long after every trace of the civilization that sent it had changed beyond recognition. The signal had been carefully encoded, a portrait of humanity compressed into 1,679 binary digits. Numbers, chemistry, DNA, a human figure, the solar system, a way of saying we are here, and we know how to speak. He watched it go. It will reach Messier 13 in approximately 24,900 years. Whatever is there, if anything is, will not receive it within any human lifetime, or within any institution's lifetime, or within the lifetime of any language currently spoken on Earth. And yet someone pointed the dish and pressed the button and let it go, because silence, to the people in that room, felt like giving up. Whether the dark forest describes anything real about the universe, we cannot say with confidence. But on that afternoon in 1974, and in every broadcast and radar pulse and deliberate transmission that has left this planet in the century since radio was invented, the question of whether to announce ourselves became less hypothetical. We called out. We did it before we understood the rules. We did it because staying quiet felt like the wrong kind of answer to a question we could not stop asking. Let that sit with you, not as fear, as the honest complexity of being the kind of thing that reaches toward the dark, even without knowing what is listening. The question of whether to announce ourselves to the cosmos is one our species answered without quite asking it. We answered it in the early 1920s, when the first commercial radio broadcasts began spreading electromagnetic signals in every direction from the surface of the planet. We answered it again in the 40s and 50s, when radar systems developed during and after the Second World War sent powerful pulses into space with every rotation of their antennas. We answered it a third time in November of 1974, when astronomers at Arecibo encoded a message in 1,679 binary digits and transmitted it toward Messier 13, a dense cluster of stars approximately 25,000 light-years away in the constellation Hercules. The Arecibo message, composed by a group that included Frank Drake and Carl Sagan, was a carefully constructed image. When decoded, it revealed the numbers 1 through 10 in binary notation, the atomic numbers of hydrogen, carbon, nitrogen, oxygen, and phosphorus, the chemical formulas for the nucleotides of DNA, a representation of the double helix, a figure of a human being, the population of Earth at the time, a diagram of the solar system, and a schematic of the telescope that sent it. It was transmitted in a single burst lasting 168 seconds. Even traveling at the speed of light, the message will not reach its destination for approximately 24,900 years. Any reply traveling at the same speed would arrive at Earth roughly 50,000 years from now. The message was sent not with any expectation of near-term response, but as a demonstration of capability and, in Drake's words, a way of saying that we are here and that we know how to speak across the cosmos. Whether that was wisdom or something more impulsive has been debated seriously ever since. The debate about whether humanity should be actively transmitting into the cosmos, a practice researchers call active SETI, or messaging to extraterrestrial intelligence, involves serious scientific and philosophical minds and has not reached consensus. Both positions deserve to be heard honestly. Those who favor transmission argue that the point may already be moot. Earth has been electromagnetically detectable for over a century. Any civilization within roughly 100 light-years with sufficiently sensitive instruments could already know we are here. Deliberate messages, in this view, change emphasis rather than disclosure. Douglas Vakoch, founder of the organization METI International, which is specifically dedicated to crafting and transmitting interstellar messages, has argued that passive listening without transmitting is a strategy that cannot work. You cannot establish contact with someone who is also only listening. Someone has to speak first. Those who counsel caution argue from a different starting point. Stephen Hawking, in multiple interviews and writings, before his death in 2018, consistently maintained that actively advertising our presence and location to unknown civilizations was a risk not adequately supported by what we actually know about the universe. His concern was not that extraterrestrial intelligence is necessarily hostile. It was that we have no basis for assuming it is not. When one civilization with a significant technological advantage encounters another, the historical record on Earth does not uniformly suggest reassuring outcomes for the lesser party. Hawking was careful to frame this as a possibility worth taking seriously, not a prediction. No international regulatory framework governs active SETI. Individual researchers and organizations can and do transmit when they choose to. METI International sent a targeted message toward Luton's star, approximately 12 light-years from Earth, in 2017. To be clear, this is a thought experiment and not a prediction. But in the hypothetical scenario where a reply was sent immediately upon receipt, it would arrive here in roughly 24 years, illustrating how different the timescales become when a target is nearby rather than thousands of light-years away. What deserves to stay with us from this chapter is not a resolution of the debate, because the debate is genuinely unresolved, and both positions are held by serious people for serious reasons. What deserves to stay is the recognition that a question of this scale, one that touches every person on the planet and potentially every person who will ever live here, has been and is being answered without the kind of deliberation its scope would seem to require. We are already visible. We have been visible for a century. The sky above you tonight is full of signals that left this planet before you were born, traveling outward at the speed of light, carrying the evidence of our existence in every direction. Whether anything is out there to notice. The silence does not say, but we are no longer waiting quietly. We stopped waiting quietly a long time ago. There is a particular kind of vertigo that comes from standing at the beginning of something, not the middle, not the end. The very first page of something that has no previous edition. Most of us are accustomed to thinking of ourselves as latecomers. Human civilization is roughly 10,000 years old, a number that sounds significant until you place it against the 4.5 billion years Earth has existed, or the 13.8 billion years the universe has been running. We arrived recently. We arrived, by cosmic standards, moments ago, and so we tend to think of ourselves as inheritors, as the latest entry in a long story that began long before us. But what if we are not the latest entry in a long story? What if we are the first sentence? The great filter argument, in its optimistic version, does not claim we were chosen or designed for this. It claims only that the sequence of events required to produce a technological civilization may be so improbable that in a universe of finite age, the first civilizations to emerge are genuinely early, not privileged, just first. The universe began approximately 13.8 billion years ago. The first generation of stars formed within a few 100 million years, but were composed almost entirely of hydrogen and helium, lacking the heavier elements necessary to build rocky planets and organic chemistry. Those heavier elements were forged inside stars and scattered across the cosmos when those stars died. Later generations of stars, enriched by the debris of their predecessors, were the first capable of hosting planets with the chemistry biology requires. Our Sun is what some researchers describe as a later generation star, formed from the enriched remnants of earlier stellar generations. The carbon in your body was forged in the core of a star that died before our solar system existed. In a strict physical sense, we could not have appeared much earlier than we did. The universe needed time to build the raw materials. Rocky, chemically complex planets around stable stars have only been common for a fraction of the universe's total age. If complex life requires several billion years to develop once conditions are right, as Earth's history suggests it might, then the first civilizations capable of looking up and asking questions may be appearing now, in this era, for the first time, not because this era is special by design, because this is the era when the ingredients were finally available and the time required had finally elapsed. We may be early not because we were favored, but because we were possible. The cosmologist Paul Davies, in his 2010 book, The Eerie Silence, explores this possibility carefully. If humanity is genuinely among the first technological civilizations to arise in the galaxy, the future is not a continuation of a story already being told by others. It is a blank page. The patterns that will define what intelligence does with the cosmos over the next billion years have not yet been established. We are not reading history. We are making it. Freeman Dyson spent decades thinking about what a sufficiently advanced civilization might eventually accomplish, staying within the boundaries of known physics. His explorations included civilizations that harvest the energy of entire stars and operate on timescales measured in billions of years. The structures such a civilization might leave behind would be detectable across interstellar distances by instruments far less sophisticated than what we already possess. We see none of those structures. Either no civilization has yet had the time to build them, or something prevents civilizations from reaching the point of building them. We are back at the filter, but standing at its edge and looking forward instead of backward. If we are first, the road ahead is open. The structures that do not yet exist, the questions that have not yet been answered, are not waiting for someone else. They are waiting for us. The philosopher Toby Ord draws a distinction between what he calls the small picture of our current moment, the daily texture of individual lives, and the large picture, in which we are a civilization barely into our technological adolescence, having just developed tools that could either end us or outlast the stars. In the large picture, the decisions made in the coming decades will determine whether the first sentence of the cosmic story becomes a paragraph, a chapter, a library, or a single sentence with no sequel. We may be the first. If we are, then what comes next is not written anywhere. Not yet. It is being written now, in the choices of ordinary people living ordinary lives, adding up across generations to something that either endures or does not. The universe has been building towards something like us for a very long time. We have only just arrived, and the page is still blank. We have travelled a long way tonight, from a quiet room and a dimmed light. We have walked through 60 years of unanswered signals, through a question asked over lunch that has never been resolved, through the vast arithmetic of planets and time, through equations that map our ignorance, through evolutionary accidents and two faces of a filter that either lies behind us or ahead. We have stood at the edge of a dark forest. We have listened to theories that span game theory and deep biology and the future of intelligence itself. Before the final chapter, there is something worth naming directly, something that has been present in every explanation we have examined without ever being stated plainly. Every explanation for the silence says something about us. Not them, us. The zoo hypothesis says we may be the kind of civilization that needs to be observed carefully before being approached, that we are, in the judgment of some hypothetical elder intelligence, not yet ready. What does it mean that we find this plausible? That when we look honestly at our own history, we recognize the portrait. We invented that hypothesis. We found it believable, because, on some level, we already understand what it would mean to encounter something powerful but not yet trustworthy, with all that contact might bring. The rare earth argument says the conditions that produced us were improbable to a degree that resists easy comprehension. What does it mean that we find this compelling? That when we look at the world beneath and around us, we see not a given, but something closer to a gift. The rare earth hypothesis is, in its deepest form, a recognition that what exists here is not the default state of the universe. It is the exception. The Great Filter says something waits on the path from chemistry to civilization that almost nothing survives. And the version that has the most explanatory power is the one in which the filter operates near where we are now, near the point where a species becomes powerful enough to end itself. What does it mean that we find this credible? That when we examine our own capabilities and our own record of using them, we already recognize the shape of a danger we have not yet fully navigated. The Great Filter is not a theory about strangers. It is a theory about what we are capable of, generated by minds that already know the answer. The dark forest says that intelligence, wherever it arises, eventually learns that silence is safer than announcement. What does it mean that this logic feels familiar? That the two axioms it rests on, survival as the primary drive and resources as finite, describe something we already know from every level of biology and history. Liu Cixin did not invent that logic. He recognized it. He applied it to the cosmos and it fit. The silence is not just an astronomical phenomenon, it is a mirror. When we ask why the universe is quiet, we are also asking what kind of thing we are, whether we are the kind of thing that lasts, whether the qualities that produced our technology are the same qualities that will eventually end us, or whether there is something in us that can turn the trajectory before it turns us. These questions have no scientific answers. Science can describe the structure of the universe and the mechanics of life. It cannot tell us whether we will choose to be wise. That is a question only the future can answer, and only we can shape. There is a word that appears often in the philosophical literature on existential risk. Trajectory, not destination, not fate, trajectory. The idea that what matters is not where we are, but the direction we are moving, and whether that direction, examined honestly, is one we would endorse. Look into the silence long enough, and what you see is not empty space. You see a species in possession of extraordinary tools and an unresolved question about what to do with them, looking out at a universe that is either waiting for them to get it right or indifferent to whether they do. The mirror does not tell you which. It only shows you what is here. What you do with that reflection is the part that is not written yet. It is late now. The thinking we have done tonight is not the kind that resolves cleanly. It does not end with a number verified or an answer filed. It ends the way the best questions always end, with a deeper understanding of the question itself, and a changed relationship to the silence that prompted it. Let us come back to where we started. You are on a planet, a small, warm, unlikely planet, orbiting an ordinary star in the outer reaches of a galaxy that contains hundreds of billions of other stars. The planet is 4.5 billion years old. Life appeared on it almost as soon as conditions allowed, and then spent 3 billion years in patient, microscopic development before anything more complex began to take shape. The complex life spent hundreds of millions of years diversifying and filling every available environment before one branch of one lineage developed the kind of brain that could hold a thought about its own existence. That brain is yours. The universe has been running for nearly 14 billion years, and you are among its results. Not the only result. There are 8 billion others on this planet alone, each of them an equally improbable chain of accidents and survivals stretching back through time to the first self-replicating molecule in the first warm pool of ancient chemistry. Every person who has ever loved someone, built something, looked up at the night sky and felt the pull of the question underneath everything we discussed tonight, was the product of that same improbable sequence. And the universe, across all of its age and all of its scale, has given no confirmed sign that it produced anything like this anywhere else. That might mean we are alone. It might mean the filter is behind us, and what we do next will be the first chapter of a very long story. It might mean the silence is the practiced quiet of many minds in a dark forest. It might mean the filter is ahead, and we are approaching something that has ended every other attempt. If any were made, it might mean something we have not yet thought of. Some explanation that will seem obvious once the right mind encounters the right evidence. We do not know. That not knowing is not a failure. It is the honest condition of a young civilization asking an ancient question with the best tools it currently has. Science does not promise answers on a schedule. It promises a method, a way of sitting with uncertainty that is more productive than either false confidence or despair, a way of keeping the question open and continuing to listen. We are still listening. The Allen Telescope Array is still scanning the sky. Breakthrough Listen is still processing data from millions of star systems. The James Webb Space Telescope, launched in December of 2021, has given us the ability to examine the light filtering through the atmospheres of distant planets with more precision than any instrument that came before it, searching for the chemical signatures that living processes leave behind. Every year, the search improves. Every year, the silence is either confirmed more deeply or one step closer to being broken. There may come a moment, possibly within the lifetime of people alive today, when something changes, when a signal holds, when an atmospheric analysis comes back with chemistry that cannot be explained without something alive producing it, when the silence ends, or that moment may not come in our lifetime. The universe is not obligated to answer on a timeline that accommodates our impatience. The question is old and may remain open for a very long time. What do you do with a question that may never be answered in the time you have? You carry it, not as a burden, as a companion. The best questions work that way. They do not resolve and disappear. They stay with you, slowly reshaping the way you see the ordinary things you encounter every day. The night sky looks different after tonight. Not more frightening. Different. More layered. More full of implication. The stars are not simply lights anymore. They are data points in the longest experiment ever run. Each one a quiet test of the hypothesis that the universe produces minds that last. The question of the silence is also, in the end, a question about this moment, about this room and this night and the fact that you are here, in it, holding thoughts that extend in every direction far beyond the walls around you. The universe did something when it produced you. It produced a being capable of asking whether it is alone. That capacity to wonder, to search, to follow the largest possible questions without demanding that they be smaller or simpler or more comfortable, is not a side effect of intelligence. It may be the point of it, not in a designed sense, not in the sense that anything intended it, but in the sense that when you follow the long chain from the first moments of the universe to this moment, from hydrogen to stars, to planets, to oceans, to the first living cell, to the long, slow climb of complexity, to the mind you are using right now to hold these thoughts, what you arrive at is a universe that has, in at least one place, become capable of contemplating itself. That is not a small thing. It is, in the most literal and unadorned sense available to us, one of the most remarkable things that has ever happened. The silence outside is still there. It will be there tomorrow and the night after. But the listening itself is something. The fact that we built the instruments and the mathematics and the traditions of inquiry that allow us to sit with a question this large and this old is not ordinary. It is, depending on how you look at it, the most interesting thing the universe has ever done. You can close your eyes now. The question will keep. It has been keeping for billions of years, running quietly underneath everything, waiting for something capable of asking it. Something finally did. That something is us. And, tonight, in whatever quiet space you have made for yourself, with the day set aside and the lights gone low and the weight of ordinary things resting for a while, you were part of the asking. That is enough. The universe is silent. But you were here. You were listening, and the fact that something was here to listen, in all the vast and ancient dark, is the most remarkable answer the silence has ever given. Rest now. The stars are still there. They will be there when you wake.